Hi, and thanks for the CCDC and BACG for ask for this talk. And I'm from School of Biological and Chemical Science, Queen Mary University of London. And this topic of this talk is the DFT-based molecular dynamic studies of electrolyte solutions, the hydrogen numbers from reorientation water dynamics. So could you please go next slide? And so natural solutions are far from the pure waters, which is rich in ions. So in solutions, ions can interact with a very degree of strength with the surrounding water molecules. So this makes solutions environment highly influential on the microscope properties of aqueous solutions. So in the case of inorganic materials such as minerals, and the dynamic properties of waters in the first coordinate shell often control the initial stage of crystal nuclei and growth. So the next slide, please. So the reliable crystal design. The reliable crystal design and operations of other industrial processes requires foundation knowledge, and that sounds theoretical understanding and accurate mathematical representation of the electrolytic systems. So please go next slide. So yeah, I will show there is a key questions concerning the effect of salt on any given solution properties is the number of water molecules affected by the ions. So I need to clear that the hydrogen number is different with a coordinate number. So the hydrogen number H is the number of water molecules influenced by the presence of the ions. So here I give a well-known aqueous electronic solutions model that contains hydrogen number H as one parameters. Here in the equations, gamma is the activity coefficient, and mu is ion strength, and AW is the activity of the water, and Ni is the number of ions generated by one solute molecules. So it is a simple theory of electronic hydrogens, and this equation combines the Debye-Hooker terms to obtain the correct limiting values of activity coefficients. But this equation is an empirical hydrogen component equations. H is the hydrogen number parameters, and A is represent the effective radius of the ions. So this model is empirical, and both the parameters A and H are getting numbers that go from the experiments data. So it's a fitting parameters. So in this project, we are going to use molecular dynamic simulations to report the structures and the dynamics of ionic solvation shells and the interaction between molecules. And the aim is that to use the physical meanings of H to get the number. So we need to get the H number from the molecular simulations, which is the number of water molecules that influenced by the ions and have different behavior from the pure water molecule. So here we call the water molecule influenced by the ions as non-bulk-like water, and other water molecules are bulk-like water. So next slide, please. So here is an overview of that what we have done. We present ab initio molecular dynamics, and because of the cost of ab initio molecular dynamics is high, we also do the classic molecular dynamics with ECC force field. That ECC force field is a different charge of the magnesium chloride and sodium and others. It's 1.5 for the magnesium, it's not 2. And then we did a lot of different analysis. The property I would like to show here today is analysis of water reorientation dynamics of the ionic solvation shells. And we also do, from the results of the water reorientation dynamic, we have implemented a new model to categorize the water molecules in magnesium chloride solutions in different subpopulations and got the hydrogen number from the water molecule here. So I will go details of this method later. So could you please go next slide? Now I will go some more details about the analysis method, water reorientation dynamic. Next slides. Yeah. And we have quantified the rotational relaxation of the water dipole. So the 0 and t is a unit vectors defining the orientations of the dipole moment of a water molecule at time 0 and time t. So the time reorientation correction function starts at 1 and then decay to 0 because of the random and isotropic orientation of the water molecule in solutions. So we use the TCFs here as the autocorrelation functions to get their relaxation time. So I will show that how these functions will be very sensitive to the type of pairs. So please go next slides. So yeah, it's now it's a result of the TCF, the left figures, but yeah, this is only the magnesium chloride. So the left figures shows orientation time correlation functions for magnesium chloride solutions at different concentration. The top figure is without contact ion pairing, and the bottom figure is that with contact ion pairing. The profile are significant influenced by the type of ion pairs present in the solution. So we can see that the top line of the figure A is 0.63 mole kilogram and 1.3 mole kilogram. It's much more similar, like the same. But in the figure B, it's a second line and the third line. So you can see there is much more difference between the same profiles, but in different with contact pairing or without contact pairing. And the right figures compare the correlation profile of the hydration mantle ion magnesium in pure water and the magnesium chloride solutions. So the decay of the profile of the water molecule directly coordinate to the magnesium are slower than that in the bulk. So for these two figures, we can tell that the correlation function is sensitive to the solution concentrations and it's sensitive to the type of pairs in solution. And therefore, we use this way to probe the cooperate the long range effective of ions on water in solutions. So could you please go next slides? Yeah, so next part, I will go present a novel approach to determine the hydrogen number H of aqueous electrolyte based on the calculation of the water reorientation dynamic. So the next slide, please. Here I will go how we define this new approach is approach to determine the hydrogen number. And the WOHH is oxygen to the first O is oxygen to the nearest magnesium, and H is a hydrogen to the nearest chloride. So because water has two oxygens, so it's a H and H. So the hydrogen and oxygen atoms of each water molecule in the solutions are depending on the position of the magnesium and chloride ions. So then the number is set to 1 when the oxygen or hydrogen atoms is in the first coordinate shell of the nearest ion, and it will be set to 2 when the atom is in the second coordinate shell of the nearest ion, and to B when the atom is beyond the second coordinate shell. We call that the bulk, so it's B. So the figure A we can see this is an example of W222 subpopulations. So the oxygen is in the second coordinate shell of magnesium, and both hydrogen atoms are in the second coordinate shell of chloride. So the figure C reports the distribution of water molecule among the 15 subpopulations. So we just got the H from these figures. So please go next slides. Yeah, here is the result. We calculate the reorientation dynamic in different subpopulations. We define the factors as a ratio between the reorientation relaxation time of subpopulations and we think that it's a bulk-like. So BBB is a bulk-like, and the figure shows the factors of subpopulations in the magnesium chloride solutions. We can use linear scale of plot the factors of different categories of the water. So clearly the first hydration shells is a W1, shows distinct factor compared to bulk water. It has almost 3 to 6 times lower dipole reorientation dynamic. And so it's easily to see that this is non-bulk like water subpopulations. Also, beyond hydration shells, water of magnesium is WB. So the B as the first number is WB11, B12, and so on. It shows very similar dipole reorientation dynamics compared to bulk-like water. However, it is a little bit tricky when we look at the second hydration shells of magnesium, the W2. So the hydration waters such as W212 and W222. So this is on the boundary edge. So we use the statistical approach to clearly classify the bulk-like water and hydration water. So the 68, 95, 90.7 rules in normal distributions, also called the empirical rules, are used here. So, and you can clearly see that the W211 and W212 is distributed way above the 3 deviations, even larger than 4 deviations. So it is reasonable to categorize as dynamic hydration water. So now the right figures, please go to the next slide. Yeah, the right figures now here shows the distribution of water molecules in the water subpopulations. So we think that the blue one is a bulk-like water, so it's more like the WBBB, and the red one is a slow reorienting waters in the subpopulation, and the summary of this is 15. So we see that the hydration number H in this concentration is 0.6 more kilogram. This concentration is 15, and which is established to see the same as one other theoretical thermodynamic models or by the visas. I don't know if, but it's a thermodynamic model and it's empirical thermodynamic models. So they use the data from the experiments to fit in the hydration number. So the H by the visas is 15, so it's the same. And please go next slide. Yeah, so using this method, use the same method we got all the H from in different concentrations from the ab initio molecular dynamic and the classic molecular dynamic, and we can compare this H with the H that we got from the experiment T-Hertz, the relaxation spectroscope, and it can be seen that at the 1.3 more kilogram, the number of bulk state water is about 13 per magnesium chloride unit. So the hydration number measured through the T-Hertz and the simulation results are well matched in high concentration simulations. But at low concentrations, the hydration number measured by the experiments fit better than with classic molecular dynamic than those of ab initio molecular dynamic. So can we go next slides? Yeah, it's now the summary of the dynamic of the hydration bound network solutions was characterized in terms of the water dipole reorientation. So the time correlation functions is sensitive to solution specialization and provide the insight into the combined effect of cations and answers on the water reorientation dynamic. So we found not only the water molecule in the first hydration of magnesium, but also that in the second hydration of magnesium and in the first hydration of chloride are found slow down. And we came out a new approach to determine the hydration number H of a curious electrolyte based on the calculation of the water dipole reorientation dynamic. And as many reactive processes involving solvent metal ions occurred in environmentals that are far from pure water but rich in ions. So I think these studies will provide a link with molecular level process responsible for affecting bulk solution behavior based on a well-defined method for the definition of the hydrogen number. So now next slide, I'll go to the acknowledgement. Yeah, I will thank the people who work with me. Thanks, Davis, to have me in his group, and for the primary research funding, and the postdoc Dimitris to help me in classic molecular dynamics simulation. And thanks to my second supervisor, Professor Simon Clicks from the University of East Anglia for the thermodynamic models part of this project. And this project is in collaboration with King from National Seoul University and his supervisors. So I will say great thanks to the UK Materials and Molecular Modeling Hub for computational resource. So this work is using the Archer UK National Supercomputer Service and the primary Apocrypha HPC facilities. Yeah, and next slide is the thanks slide and questions.
Thank you so much, Xiangwen. I think we did have a couple of questions come in the chat box.
Okay.
Eleanor, did you double check what we've got?
Yeah, so Xiangwen, Martin is asking if the concentration of magnesium chloride used in the calculation is close to the saturation concentration.
Yeah, we use a high concentration. I think it's up to 6 molality, but there is only the magnesium chloride in the water. Is no other ions.
And what's the solubility at the temperature you're?
The temperature is 25. It's a room temperature.
Yes, but so is it saturated or is it close to the saturation to the solubility? I think that's what Martin is asking. I think Martin doesn't have a mic.
I think it is, but it's just I think the 2.3 more kilogram is much more like the it's much more like the saturation concentrations. But the under, because when we have 40 unit more magnesium chloride in the solutions, we have 700 waters. That is the saturate concentrations.
Okay, thank you.